This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning. So as I said yesterday, we will skip one lecture, which I will come back to at the very end. So we will push on with the frequency domain compensation. So today I will talk about performance specifications. So the first step when you are doing controller design via body diagrams is to translate your performance specifications into the desired shape of the compensated open loop transfer function body diagrams. So you have body diagrams that you sort of have for the plant. You will have to add the compensator, controller body diagrams to get the body diagram of the open loop transfer function, and that body diagram needs to satisfy certain constraints on its shape. And these constraints come from the performance specifications. So today's lecture is all about translating performance specifications into constraints on the shape of the compensated body plots for the open loop transfer function. All right. So as usual, I first motivate things a bit, then I will talk about performance specifications in frequency domain. You will see that you can, for instance, relate the shape of body diagram to perhaps rise time or overshoot. So you can also relate shape of body diagrams to steady state errors. So we will go through all of these different possibilities, and we will talk about how, to impose certain constraints on these diagrams, body diagrams, to achieve certain performance specs. So, and then I will also talk about some fundamental limits. Now, we talked about fundamental limits already when we talked about, let's say, undershoot. We saw that unstable zero would always result in undershoot in the step response. Now, you also can state certain fundamental limitations in frequency domain. And you will see that if you, for instance, try to shape sensitivity function at low frequencies to achieve better disturbance rejection, like low frequency disturbance rejection, or better tracking of references, that would result into increase of sensitivity at higher frequencies, which may be undesirable. So there is this trade-off again in frequency domain, and we will talk about this sort of fundamental limits. This is sometimes referred to as body integrals. So there are certain equalities that are called body integral equalities, which specify this sort of fundamental limits to what is achievable when shaping your open loop response. So, sorry, the sensitivity transfer functions frequency responses. And then I will wrap up with the conclusions. All right, so So just a bit of an overview of what we already did and just sort of motivation for this lecture. First, body plot of the open loop transfer function can be related to a range of performance specifications. We did, for instance, talk at the end of last lecture about steady state errors. So we saw that the shape of the open loop transfer function body plot, magnitude plot, is related to steady state errors. Right? So we will do more of that in today's lecture. So what is the idea? The idea is to shape open loop transfer function to achieve required design objectives. So your boss comes and tells you, okay, you need to satisfy this with your control system. You need to design a controller. So that will impose certain constraints on the shape of the body diagram for the compensated open loop transfer function. So we will need to learn how to do this. And then, since this is the body plot of the open loop transfer function is a sum of body plots of the plant and controller, we can pick controller to compensate the plant dynamics. So that's the idea behind loop shaping. Sometimes this design strategy is called loop shaping because you are shaping the loop of the open loop transfer function to achieve certain performance specifications. All right. So we will now spend some time talking about performance specifications. By the way, I will refer to some formulas that we already covered and some diagrams that we've already covered, but I will also introduce some new diagrams that will be used to translate performance specifications into the sort of constraints on the body plots for the compensated system. All right. So here is the summary. So first, I'll summarize how we can relate certain performance specs to the shape of body diagrams, or which frequency regions are important. So if you plot, so what is plotted here is the phase and gain of the open loop transfer function. So I remind you that lambda 0 is the open loop transfer function, is the product of the controller and plant. So C times G0, that's lambda 0. So what we are plotting here is the gain plot, the top diagram, and the phase plot of the open loop transfer function. So what we will show in today's lecture, and we already mentioned this in previous lectures, some of these things, that the gain characteristic of the open loop at low frequencies will be possible to relate to tracking. How well do we track step references or ramp references or different types of reference signals? And it would also be, it's all about steady state, right? So tracking of different reference inputs and steady state behavior. If you look at the region around the crossover frequency, by the way, the frequency at which magnitude of in the body plot is 0, right? That's the crossover frequency. That's the point where Nyquist plot crosses which point or line or circle. What does this point correspond to in Nyquist plots? Does anyone remember? So circle of radius 1 centered at the origin, right? Yeah, so because at that point, at that frequency, the gain is 1, so when I take logarithm of 1 of 0. Right? So that's what this frequency corresponds to. We will see that what happens for the phase and the crossover frequency around this range, that would be possible to relate to transients, in particular overshoot and rise time, right? And also stability. So at this frequency, we will be looking at the phase margin. So this would be like the amount of phase margin in this example, and that is related to stability, right? So stability would be possible to check, and also the properties of the transients. So when you apply step response, you look at the transients. So properties of these transients will be possible to relate to So what happens around this frequency? And finally, the high frequencies, what happens at high frequencies will be related to robustness, especially to measurement noise, also disturbance rejection. So these things are then covering a lot of different aspects of performance and robustness. So when you look at what we can address here by shaping body plot, we can address steady state errors and tracking, we can address stability and transience, we can address robustness with respect to high frequency signals. So you can see from just this summary that we here have a very powerful tool that can address in one go a range of different requirements on the performance and robustness of the control system. Right? So what we will do next is go step by step. First look at low frequencies, then high frequency, crossover frequency region, and then high frequencies, and then present more specific analysis and formulas or diagrams that you can use when translating performance specifications into the shapes of body diagrams for the compensated plot. Right? So let's first talk about what's happening at low frequencies. Let's talk about steady state errors and tracking. All right. So what we learned already from Laplace, transforms and internal model principle, is that if you want to track or have zero steady state error for step reference signals, your open loop transfer function has to contain an integrator. So controller in particular should contain an integrator, if the plant doesn't have one already, right? So this we learned from internal model principle. So what does this imply? Well, this implies a constraint on the open loop gain at low frequencies. Gain plot needs to be above -20 decibel per decade at low frequency. Why is this? Well, if the open loop transfer function, if the controller contains an integrator, right, which is necessary, we saw that an integrator is necessary for zero steady state error, for tracking step references. When we are plotting the open loop body diagram with an integrator, we would be adding the body plot of the integrator with something else. There will be lots of other stuff, right? But the integrator itself would impose this constraint, because we are graphically adding body plots of constituent transfer functions for the open loop. So open loop is a product of some basic transfer functions for which we know body plots, and then we will just add them together, right? So if you have an integrator, what is the body plot of an integrator? Does anyone remember? It's just a sort of magnitude is going down, right? So I'm talking about magnitude. So it's just going down at -20 decibel per decade. So that's why, oops, sorry about that. That's why we would, if we are adding anything else to sort of that body plot for the integrator, then we will have to be above some line that is -20 decibels per decade, right? And that means that this guy here would have to be above a line that is determined by some sort of integrator body plot, right? So also, if we want to achieve good tracking for low frequency references, or attenuation of low frequency output disturbances in some frequency band between 0 and x, then we will have to have that the gain is very large. So what does this mean? Well, gain is larger than some n, which is much larger than 1, for all frequencies on this frequency band on which we want to have this tracking or disturbance rejection, right? So this is what we saw also from the previous analyses in the previous lecture. So in other words, on this region of frequencies on which you want to have good tracking of references at these frequencies, right? The complementary sensitivity gain should be close to 1 and sensitivity should be close to 0. Right? So we again saw this from the previous lecture. So what does this translate into? Well, you may have, for instance, for integrator, you know, if you want to track step input signals, then you have to have an integrator. Then that sloped line there is the boundary, and you have to be above that such a boundary, right? That's because you want to track step references with zero steady state error. And then if you want to track all the reference signals between 0 and x, you have to push the gain to be above some number m. This m would be related to the steady state error that you would be making, right? The larger the m, the smaller the steady state error that you would be making for all signals in this frequency band. So for all signals of this frequency band, you know, m is roughly inversely proportional to the steady state error that you would be making, you know, when tracking these signals. So by the way, if we want to track ramp signals, the slope should be minus 40 decibels per decade. Why is this? Because of the internal model principle, we have to have a double integrator. So double integrator, we add two integrators, you know, gain, so it's then minus 40 decibels per decade, right? So this gives you, you know, pretty good sort of set of guidelines on how to shape the open loop transfer function by the choice of controller, right, in the low frequency range. So I give you some set of specifications, then you can translate them into this sort of forbidden region. So in this case, you have to be above this region for low frequencies. So body magnitude plot should be above this colored region to satisfy the given set of performance specifications. Okay? We're doing something similar we did for locations of poles, where we talked about, you know, okay, overshoot, you know, poles have to be, you know, in this region. Rise time, poles need to be in this region. Settling time, poles need to be in this region. Here we're doing something similar. I'm telling you, if you want to have certain tracking properties, or, you know, steady state errors, right, then body plot, magnitude plot of the open transfer function should satisfy this constraint. All right, so now we can move to this region around the crossover frequency, and the claim is that this region would be related to stability of the closed loop and also transients. In particular, we would be able to talk about overshoot and rise time by looking at what's happening around this crossover frequency. By the way, when I say crossover frequency, I mean not just magnitude plot. What's happening here is also important for the phase, right? Okay, so let's now look at this. So suppose that you are given a requirement. You are told your overshoot should be smaller than, let's say, 10%, and your rise time should be smaller than, let's say, 1 second or 0.1 second. What is possible to do, it's possible to translate these requirements into the shape of body diagrams, both magnitude and phase plots. And we will learn how to do that. So suppose that you are given a constraint on the overshoot. By the way, I'm using MP for overshoot, like that's the notation for overshoot. And this is the rise time. So if I'm given some X and Y, your boss tells you, well, X should be, you know, less than, you know, 0.1 or whatever, and this is less than 0.2. Then that would be possible to translate into phase margin being larger than some number determined by, well, this required overshoot. And also the crossover frequency should be larger than something that depends on the overshoot and the rise time. So we will present now diagrams or formulas that are derived for second order systems. So it's like a canonical second order transfer function, but these are often used as a rule of thumb for higher order systems, similar to what we had with Laplace domain designs, right, root locus and things like that. So similarly, we would use rules of thumb derived for lower systems, right? Formulas derived for lower systems would be used as rules of thumb for higher order systems. So let's look at what these diagrams look like. So, by the way, you saw already a diagram that looks like this. So this is the overshoot, and this is the damping ratio for second order systems. So we saw that you can plot something that looks like this. So basically, if I tell you I want overshoot less than 10%, I go basically, I say 10%, I go all the way to this curve, and then I read out what is the damping. Well, damping, perhaps if I pick 0.6, I will be below 10%. You can see that from this diagram. We presented this diagram before, right? Okay. What we also can do, and this wasn't done before, we can relate the damping ratio for second order systems to the phase margin. So what's the phase margin? I remind you, the phase margin is you look at the crossover frequency, and then you look at how much sort of larger or smaller this phase is from minus 180 degrees. So what is plotted here is a positive gain margin because we are above minus 180 degrees. But if this went below, then it would be a negative phase margin. That would actually correspond to an unstable system. So suppose that you do not have any poles in the open loop transfer function that are in the right half plane. What is the Nyquist criterion for stability in that case? That's the special case. So the open loop transfer function is stable, no unstable or on an edge axis open loop poles. Shouldn't encircle the critical point. What is the critical point? Right? So -1 J0. So -1 J0, note that if I draw a circle centered at the origin, right, which has radius 1, that would pass through the critical point. What is the crossover frequency? The crossover frequency is exactly the point where you cross that circle, right? So the circle of radius 1 centered at the origin. So if you cross this circle at the point where phase minus 180 degrees, what does this mean? You passed through the point -1. What if this phase is smaller? Right, so you can see you did not encircle the critical point. If this phase is larger, you have encircled it, right? So for that special case, phase margin tells you first about stability, but also we saw it gives you a degree of robustness margin. How far are you from becoming unstable? Because what's phase margin? It's the amount that the angle you need to rotate the Nyquist plot so that it passes through the critical point, right? So what is possible to do is, well, you can relate phase margin actually to the damping ratio for second order systems. And this is given in this diagram. So MF is the amount of phase margin. In this diagram, it's given in degrees. So you can see, for instance, that if the damping ratio is 0.2, you will have phase margin of about 22 degrees, right, from the diagram, okay? So this is basically telling you what happens for second order systems, right? So this is second order systems. We will use these diagrams as rules of thumb for higher order systems. But this is exact diagram for second order systems. So what is also given in this picture is this dashed line. Now why do you think I have this dashed line here? Yep. Very good, thank you. So it's an approximation of what the phase margin curve does on this range. Maybe from 0 to 0.7 roughly, you would make a small error if you approximate this relationship with just this dashed line. So for all the damping ratios between 0 to 0.67, right, it's possible to use 100 times the damping ratio, that's your phase margin, right? That's just useful as an approximation. Now, once you sort of fixed your, let's say, overshoot or damping ratio to satisfy certain phase margin and transients. By the way, by playing with this overshoot now, you can see, the damping ratio, you can see you're affecting both overshoot and phase margin. Note, as you have less and less phase margin, right? So here, phase margin is very low, damping ratio is low, overshoot is high. As you are getting closer and closer to instability, you are getting worse and worse response. You have larger and larger overshoot. So you can really see now relationships between these different things in frequency domain and time domain, right? So this diagram is very useful for that reason. So once you fixed, so suppose you fixed, I don't know, damping ratio around 0.3, well, you would have, you know, a phase margin of about 45 degrees and, you know, overshoot about also 45%, right? You can then say, well, suppose now I also want to satisfy a condition on certain rise time. So I give you rise time you want. We saw from Laplace domain analysis that for second order systems, the natural frequency should be larger than something like this. You remember there's this semicircle of radius omega n, and you have to be outside of this circle, right, in the left half plane. Now, there is another diagram here that says, well, if I fixed my damping ratio with phase margin, phase margin and overshoot, and I gave you this sort of constraint on rise time, there is another diagram that now relates damping ratio with normalized frequency. So what is this normalized frequency? It's what's plotted is crossover frequency divided by omega n. So if I told you what rise times I want, right, then I can obtain what natural frequency constraint you need to satisfy. And then if I already fixed the damping ratio to fix these guys, then I can read out, okay, damping ratio should be this, then omega c over omega n is this, so I can calculate what crossover frequency is from the requirements on overshoot and rise time. Does everyone follow that? Yeah? Okay. So now, going back to my original claim, well, whatever is happening in this region, both in the gain and sort of phase characteristics around the crossover frequency, is related to stability and transience. So by moving the crossover frequency, we will be, you know, and ensuring certain phase margin and those frequencies, we will be affecting the overshoot, rise time, and also stability. So we are ticking off a lot of boxes by sort of imposing certain requirements on the phase margin, which is related to the damping ratio, right? And also crossover frequency, which is now related to the rise time as well, right? So all of these can be done as a sort of first step in figuring out what you need to achieve when you are doing frequency domain compensation, right? So I tell you, all right, get this overshoot, get this rise time, and then you will figure out what sort of crossover frequency region you need, what sort of phase margins you need, right? So that's how things would go here. All right. So that's just summarizing the whole thing. So to get sufficiently small rise time with given overshoot, crossover frequency needs to be sufficiently high, and to get sufficiently small overshoot, phase margin needs to be sufficiently large. So that's exactly what we saw from the previous diagram. And all of this is happening in the region of crossover frequency. And finally, we can talk about high frequency. So we now want to talk about robustness, what's happening here. So to reject disturbances in a certain high frequency range, we know that complementary sensitivity needs to be very small. which means that open loop gain needs to be sufficiently small in the same frequency band. So if we have that the gain, open loop gain, is close to 0 for some frequency range, large frequencies, then we know that this will imply that complementary sensitivity gain is also small. And that's good for rejecting measurement noise. So we did that last lecture, right? We talked about this last lecture, right? So that's what we get. So we have basically a region. So you have this box. So you tell me, or your boss tells you, well, which frequency, for which frequency range you want to be robust in terms of measurement noise. Usually you're saying for all frequencies larger than this. Then your open loop gain should be sufficiently small in all of this frequency region to achieve sufficient attenuation of measurement noises in that region. Right? So basically your gain of the open loop transfer function should be below this colored box. Right? In this frequency range, the open loop gain should be below this frequency box. Why? Because it should be, so we have to have this satisfied. Open loop gain is sufficiently small, close to 0, for all frequencies larger than this x. That implies from our approximations from the previous lecture that complementary sensitivity is close to 0. And that implies that we have good rejection of measurement noise for all noises in this frequency range. All right, so this is what we get. This is like Persian carpet, lots of detail here, but it summarizes everything we said so far, right? So if I give you performance specifications in frequency domain, then you will be able to come up with these some red box, which might be either box or it may have certain slope on top, and the gain characteristic would have to be above that in order to satisfy certain tracking properties. Around crossover frequency, we will be ensuring stability, so you will usually be given some value of required phase margin, or you will be told you need to make overshoots smaller than this, which you can translate into requirement on phase margin. So you want phase margin to be above that, right, comfortably above that. And then crossover frequency is related to rise time. Where exactly it is, it's related to rise time, right? So again, the rise time requirements can be translated into the region of where crossover frequency should be, right? And then for rejection of high frequency noise, you would need that your gain is well below 0 decibels in order to ensure, on a certain frequency range, in order to assure robustness to measurement noise in this range of frequencies. So you see, you would, any problem of compensation in frequency domain would require this step. This is the first step in any design. The first step is to translate certain set of performance specifications into the constraints or the shape of the phase and gain plots of the open loop transfer function. Note here, we are talking about open loop transfer function, but we've already related how it affects all the sensitivities, right? So we use some of these relationships to actually come up with this. Right? So whenever you are given a problem like this, you would first need to figure out, okay, what are the constraints of the frequency sort of body plots in each range of frequencies. It's a very powerful, that's why I was telling you, you remember I was telling you early in this subject that when we come to body diagrams and loop shaping, that this is the most powerful technique you will learn in this subject. Why is this? Well, in Laplace domain, we could not talk about robustness in any meaningful way, whereas here we can. Right? So, but here we can also talk about steady-state errors, and we can also talk about transients, and we can talk about stability. So this is a much more comprehensive tool than what we could do with root locus, for instance. I mean, root locus has its place, and it's very useful, and it gives you a lot of intuition, and it sometimes does the job. but this gives you much more, it kills more birds with one stone. Right? So it's much more powerful than what we did before. All right. Are there any questions regarding this? No? Okay. So you will need to start using frequency domain compensation for your labs soon, if you haven't done that already. So you need to do lead lag compensation in the labs. That's why I'm rushing to get to that point. So you see at least one. So this week we will see at least one compensated design, and that's good. Already you know what's going on. This is already going to give you. What's this? Sorry about that. Oh, come on. All right. All right. So the last topic I want to cover in this lecture is so-called fundamental limits in frequency domain. I will not prove anything. I will just state the result and explain its consequences. Right. So it's a very, very interesting sort of fundamental limit. You cannot beat it. So no matter how you design your linear controller, you cannot beat this fundamental limit. Right? So that would impose real constraints on what's achievable through this design. By the way, when I tell you, okay, you need to achieve something like this, actually there are limits to what's achievable. So there may be situations where I give you a set of specifications that are unachievable. You cannot achieve it, no matter how you design a controller. And these fundamental limits that we will see next present a little bit of intuition of what's not achievable, or they tell you exactly what's not achievable, right? Okay, so, well, there are fundamental limits, I already said that. The limits are best captured by the so-called body integrals. We will present only one of such integrals. So there are many others. So there are books written exclusively on fundamental limits to, let's say, linear control and estimation. And in those books, you may find catalogs of various fundamental constraints or fundamental limits. So we are presenting only one, but this is a tip of an iceberg. So there's lots of other fundamental limits you can state in frequency domain that we are not stating here. All right. So what does this constraint that we will consider states? Well, it states that if we reduce sensitivity gain, we're talking about sensitivity transfer function, not open loop gain, sensitivity transfer function. So if we reduce sensitivity gain on low frequencies, and we would like to do that for low frequency output disturbance attenuation and reference tracking, this will lead to an increase of sensitivity gain at high frequencies, which means that we will be more sensitive to some disturbances at high frequencies, right? So, or we will not have tracking of high frequency reference signals, right? So there is a fundamental limit to this, and it's really well captured by this picture. This is taken from a so-called Bode lecture by Gunther Stein in 1989. Bode lecture is a big deal. So this is the most important plenary lecture in conference on decision and control. This is probably the most important conference on control theory, right? So there will be maybe a couple of plenary lectures, but Bode lecture is a very important one. So there's like a competition, and then people who are really the big names in control, they present such Bode lecture. So this is taken from such a lecture by Gunther Stein. So what he's saying basically, if you think about, so let me first explain what this picture says. If you are working hard to reduce the gain of the sensitivity transfer function at low frequencies, you will be piling up this gain somewhere else for a large number of systems, for a large class of systems. So why would you be reducing sensitivity gain here? Well, low sensitivity gain at low frequencies means that complementary sensitivity gain is close to 1, which means that you get good reference tracking. But low sensitivity gain also at low frequencies means that you will be rejecting well the output disturbances at those low frequencies. So it does two things at the same time. helps you with reference tracking. You get small errors, steady-state errors, and it really attenuates the output disturbances at these low frequencies. But what does this fundamental limit say? Well, if you are working hard to design your controller to make the gain slow at low frequencies, you will be piling up that gain somewhere else. There's some sort of preservation of gain. And the precise formula is given there, so it's precise statement. So it says there, suppose that the open loop transfer function has no poles on the imaginary axis or in the right half plane. So basically, open loop transfer function is stable, right? So that this ln of norm of S0 is the sensitivity transfer function, which is by definition minus ln 1 plus lambda 0. Why this minus? Why this minus? Yeah, so sensitivity is 1 over 1 plus lambda 0. That's why I have this minus. So because of this assumption, you know, this function will be analytic on the imaginary axis in the right half plane. And suppose that relative degree of the open loop is greater than 2. These are all assumptions. But these assumptions cover a large class of systems. A large class of systems will satisfy these assumptions. And then it says, Bode integral states that then, if that's the case, then the integral from 0 to infinity of ln norm of S0 d omega is 0. What does this mean? Well, you know, when you look at the area of this ln norm of S0, right? Well, that may be either negative or positive, depending on whether the gain S0 is smaller than 1 or larger than 1. So basically, the areas above 1 and below 1, right, or below 0 and above 0 with decibels, right, should be 0. That area, when you integrate overall frequency, should always be 0. So if you are reducing the area here, which is basically below 0, you are piling it up somewhere else where sensitivity is above 0. You see, that's the sort of consequence of this Bode integral. So, and this is true no matter which controller you pick. So you have your Planck transfer function, and you are trying to design a controller, and you are trying to satisfy certain performance specifications. Well, lots of specifications would require that sensitivity is small in the low frequency range. By the way, how do we achieve this? By shaping the open loop transfer function. Open loop transfer function should be what? High, large, very large. Yeah? So large open loop transfer function gain would result into small sensitivity transfer function gain, right? So if you are working hard to reduce the sensitivity gain in low frequencies, you will be piling that up somewhere above 0, where this area is positive, right? And this would hurt you. So this is while you are making something that's desirable here, this is often very undesirable, right? What does this tell you? Well, this tells you that control design is an art. It's not easy, right? And you need to be really skillful to do your best, to satisfy certain performance specs. And sometimes you need to also know, well, it's impossible to do certain things. All right. So, are there any questions? By the way, this is called the waterbed effect. So sort of it's like a wave, it reduces on one side, it increases in another side. Any questions regarding this?
Or you can just move the peak like as large device high frequency.
Depends on the plant and your specific situation. So this is giving you a qualitative constraint which you cannot avoid. Now, where exactly this peak would be and where you can place it, that depends on the specific example. Yeah. But it would exist somewhere. Yeah. Any other questions? Okay. So, by the way, these sort of integral constraints or Bode integrals they can be stated for open loop poles on the imaginary axis. It actually becomes a positive integral constraint when there are some open loop right half plane poles. What is the positive integral? Well, it means that this integral here is no longer zero, but it is related to unstable poles, right? So it's no longer zero, but it is positive. It is positive. And that is even worse because there is more area above zero than below zero, right? So you can see just from that fact that unstable open loop poles would make your design harder. So if you have an unstable plant, you will inherit, open loop transfer function inherits those unstable poles, right? We will not be canceling with controller unstable poles, right, of the plant directly. We talked about why not before, but if you have unstable plant poles, this results in a positive integral, and that means the design is even harder. So this implies, I already talked about it, implies peaking of the sensitivity when there is an upper bound on open loop gain crossover. So if you want to have an upper, like a upper bound on crossover frequency, for some reason, we talked about different specifications. So sometimes you might say, I do not want my crossover frequency to be above this point, and your design is respecting that constraint. Well, if you have such a situation, then this will result in the sensitivity peak, definitely, right? All right. So just to wrap up, so what we did today, we looked at performance specs from time domain, right? And translated them into performance constraints of the body diagrams for the compensated open loop transfer function. And we saw that low frequencies are related to tracking and steady state errors. Around crossover frequency, we saw that transients, in other words, rise time and overshoot, and also stability, they are related to it. By the way, the phase margin is a measure of robustness. So also robustness is captured by what happens around crossover frequency. Robustness in some sense, right? And then for high frequency, we have disturbance rejection and robustness. And we also saw that there are some fundamental limits to what is achievable through control design. Okay. Are there any questions? All right. Tomorrow we will cover the first sort of types of compensators. I will go through different types of controllers that we will use in this context. And then we will start with compensator design. So you will see the first compensator design tomorrow. All right, thank you. I'll see you tomorrow.
Within? Yeah.